Your server is being attacked right now. Not maybe, not eventually. Right now, as you read this, somewhere out there, an automated bot has already tried your IP address, checked if port 22 is open, and attempted a login. The question isn't whether attackers are coming for your Linux server. The question is whether you've made it easy enough for them to succeed. Most people who lose their servers to hackers didn't make one catastrophic mistake. They made 5 small, completely avoidable ones. Default settings they never changed, tools they never installed, software updates they kept pushing off, and by the time they realized something was wrong, the damage was already done. Ransomware encrypted, data gone, cryptocurrency miners draining electricity, their infrastructure silently serving someone else's criminal operation. I'm going to walk you through exactly what's putting your server at risk, and more importantly, exactly how to fix it. This is the stuff that actually matters. If you're new to Nolan Tech, make sure to subscribe and turn on notifications because we upload new tech videos regularly that help you stay ahead. Let's start with something that happened not long ago. A mid-sized company, nothing flashy, just standard business infrastructure running on Ubuntu, thought they were secure. They had passwords, decent ones actually, but they had never touched their SSH configuration. Default everything. Within a few months, unusual processes started appearing in their system metrics. By the time their team investigated properly, attackers had already dug in deep. Root access, cryptocurrency miners running in the background, their servers quietly enrolled in a botnet, doing someone else's dirty work while the electricity bill quietly ballooned into thousands of dollars. The investigation took weeks, the rebuild took longer, and the truly painful part, every single thing that happened to them could have been stopped by spending 1 hour changing 5 settings. That's what we're doing today. Before we get into those settings, though, you need to understand something about the threat environment you're operating in. SSH vulnerabilities aren't just theoretical attack vectors that security researchers write papers about. They're active, real, and they affect software that millions of servers are running right now. In early 2025, the Qualys threat research team uncovered 2 serious flaws in OpenSSH itself. The first, tracked as CVE 2025-26465, allowed attackers to intercept SSH sessions under certain conditions, specifically when a feature called Verify Host Key DNS was enabled. That's a man-in-the-middle scenario where someone sits between you and your server, silently watching everything. The second flaw, CVE 2025-26466, was a denial-of-service vulnerability that could crash your server through memory exhaustion. Both issues affected OpenSSH client versions stretching from 6.8p1 all the way through 9.9p1, nearly a decade's worth of deployed versions sitting on systems all over the world. OpenSSH maintainers moved fast and released version 9.9p2 to patch both. But here's the thing about patches. They only protect you if you actually install them. Then, in April 2025, a vulnerability turned up in Erlang's SSH implementation that scored a perfect 10.0 on the CVSS severity scale. That's the maximum. A flaw that allowed completely unauthenticated remote code execution, meaning an attacker didn't need credentials, didn't need to guess a password, didn't need anything except network access to your server. They could send specially crafted messages during the SSH handshake and execute arbitrary code as root. Security researchers noted that this particular flaw required no memory corruption techniques, no advanced exploit chains. Basic knowledge was enough. Proof of concept code was circulating almost immediately after disclosure. And later in 2025, CVE 2025-61984 demonstrated that even the proxy command feature in OpenSSH could be weaponized, allowing attackers to inject malicious commands by manipulating usernames with control characters. The pattern here is clear. Even mature, widely trusted software like OpenSSH has vulnerabilities. The difference between a server that gets compromised and one that doesn't often comes down to whether the administrator was paying attention. With that context in mind, let's talk about the actual mistakes that are leaving servers wide open. The first one is running SSH on port 22. Port 22 is SSH's default. Everyone knows it. Every attacker's tool knows it. Every scanning bot probing the internet knows it. Right now, there are millions of automated scripts continuously sweeping through IP address ranges looking specifically for port 22. They're not sophisticated operations run by skilled hackers sitting at keyboards. They're just scripts. Dumb, relentless scripts that try thousands of username and password combinations against every server they find. When security researchers deploy honeypot servers, deliberately exposed machines designed to study attack patterns, they see thousands of connection attempts within the first few hours of going online. Not days, but hours. And almost every single one of those attempts targets port 22. Now, I know the counter-argument. Changing the port is just security through obscurity, and on its own, that's true. It doesn't make your server fundamentally more secure, but security isn't one measure. It's layers. A sophisticated attacker who specifically wants your server will scan all 65,535 ports and find SSH wherever you put it. But the reality is that the vast majority of attacks aren't targeted. They're opportunistic. Bots are looking for low-hanging fruit, and low-hanging fruit lives on port 22. Move SSH to something in the range of 1,024 to 65,000, and most of those automated scripts move on to easier targets. Your logs get quieter. Your server stops wasting compute resources, processing thousands of failed authentication attempts. You become significantly less visible to the noise. It's not an invisibility cloak. It's removing yourself from the automatic target list. Changing the port is simple. Open your SSH daemon configuration file. That's at config. Find the port directive and change it to whatever number you've chosen. Just make sure your firewall is updated to allow connections on the new port before you restart the SSH service, or you'll lock yourself out. More on that in a moment. The second mistake is allowing root login over SSH. This one is genuinely dangerous, and it surprises me how many servers still have it enabled. Here's the problem. Root is the super user on every Linux system. It has unrestricted access to everything. And because it exists on every Linux installation, attackers already know half of what they need: the username. They don't have to guess it, they just need the password. Brute force tools like Hydra and Medusa can hammer away at the root account automatically, cycling through massive lists of common passwords, dictionary words, and combinations from credential databases leaked in previous data breaches. If your root password is anything short of genuinely random and long, it's a matter of time. And even if your password is strong, even if you're confident no one can guess it, why expose that attack surface at all? The correct approach is to create a regular user account with a unique username that doesn't appear in any attacker's word list. Give that account pseudo privileges so it can perform administrative tasks when needed. Then set permit root login to no in your SSH configuration and restart the service. Now an attacker has to correctly guess both the username and the password. That's not twice as hard. That's exponentially harder. There's also a practical security benefit beyond just blocking unauthorized access: accountability. When someone logs in as root, the logs just show root. You have no idea who that was. When users log in with individual accounts and escalate with sudo, every command is tied to a specific identity. You can audit exactly who did what and when. If something goes wrong, whether it's an accidental misconfiguration or an actual intrusion, that audit trail is invaluable. I looked into a case once where attackers gained root access through a brute force attack. The password was admin plus 7 characters. The compromise happened within 2 hours of the attack starting. By the time anyone noticed anything, the attackers had installed a backdoor, created additional user accounts, and set up persistence mechanisms to maintain access even if the original entry point was discovered and closed. Rebuilding that server from scratch took weeks. Disabling root SSH login would have prevented it entirely. The third mistake is relying on password authentication instead of SSH keys. Passwords are convenient. I understand the appeal. But for SSH access, they're fundamentally the wrong tool. Every time you authenticate with a password, you're staking your server's security on a secret that can be guessed, phished, found in a breached database, captured by malware, or simply forgotten and reused somewhere it shouldn't have been. SSH key authentication works completely differently. You generate a key pair, a private key that never leaves your machine, and a public key that you place on the server. When you connect, the server issues a cryptographic challenge that can only be answered by someone holding the private key. The private key itself never travels across the network. What travels is a signature that proves possession of the key. Forging that signature is computationally impossible with modern hardware. To give you a sense of the scale, a 4096-bit RSA key has approximately 2 to the power of 4096 possible values. Brute forcing that isn't just impractical, it's not going to happen in any realistic scenario, not with today's hardware, not with tomorrow's hardware. The math simply doesn't work in an attacker's favor. On top of raw strength, SSH keys solve practical problems that passwords can't. They can't be phished. You can't accidentally type your private key into a fake login page because it's never typed at all. They don't appear in log files. They can be scoped to specific purposes. A key for work servers, a separate key for personal infrastructure, another for automated deployment scripts. If one key is ever compromised, you revoke that key. You don't have to rotate credentials everywhere. Setting this up takes about 5 minutes. Run SSH keygen on your local machine to generate the pair, then use SSH copy ID to push the public key to your server. Once it's working, go into your SSH configuration and set password authentication to no. At that point, password brute force attacks become completely irrelevant. Attackers can throw millions of password attempts at your server and accomplish nothing, because the server won't accept passwords regardless. Keep the private key protected with a strong passphrase and back it up. Generate additional key pairs for backup devices if you want extra redundancy. Losing a private key and being locked out of your own server is a real and painful scenario, preventable with a bit of planning up front. If you're enjoying this video and finding it useful, take a second to like the video and subscribe to Nolan Tech. It really helps the channel and lets us keep making detailed tech content like this. The fourth mistake is not running fail2ban or something comparable. Even with everything we've covered so far, custom port, no root login, key-only authentication, attackers will still probe your server. They'll scan for your SSH port. They'll fire connection attempts. They'll test for misconfigurations. You need a system that detects this behavior and responds to it automatically without you having to babysit your logs. That's what fail2ban does. It watches your authentication logs in real time. When it sees multiple failed login attempts from the same IP address within a defined time window, it automatically creates a firewall rule to block that address. The attacker gets cut off. No manual intervention needed. The configuration is straightforward. After installing fail2ban, you create a jail configuration for SSH. A typical setup might allow 3 failed attempts within a 10-minute window before banning the source IP for an hour. You can tune those numbers to your situation. More aggressive settings for high-value servers, more lenient settings if you want to reduce the risk of accidentally blocking legitimate users who fat-fingered a password. Make sure the port setting in your fail2ban jail matches whatever port you moved SSH to. Point the log path at your authentication logs, usually var log auth dart log on Debian-based systems. Set your max retry, ban time, and find time values, and you're done. From that point on, fail2ban works silently in the background, dropping attack attempts before they can accumulate into anything meaningful. On servers that see significant traffic, fail2ban regularly blocks hundreds or thousands of IPs over the course of a month. All over the world, all automated, all blocked without any human response required. It's one of the highest return security tools you can install, and it takes 15 minutes to set up. The fifth mistake is running outdated SSH software. I opened this video by walking through a series of serious OpenSSH vulnerabilities discovered across 2025. Every one of those had a patch released. The administrators who got compromised weren't necessarily running exotic configurations or making obvious mistakes. In some cases, they were simply running software that hadn't been updated. Attackers maintain databases of known vulnerabilities. They have automated tools that scan for version strings and flag unpatched systems. When they find a server running a version with a known exploit, they use it. The sophistication ceiling for this kind of attack is low, which means it's available to a much wider range of threat actors than truly novel exploits. Keeping SSH updated isn't a nice to have, it's the baseline. On Debian and Ubuntu-based systems, that means running sudo apt update followed by sudo apt upgrade regularly. On Red Hat, CentOS, or Fedora systems, it's sudo dnf update. Most distributions offer automatic security updates that can apply patches as soon as they are available, worth enabling for critical packages if your environment supports it. Beyond just running updates, subscribe to security advisories. The OpenSSH project maintains a mailing list. Keep an eye on CVE announcements relevant to your stack. When a critical vulnerability drops, you may need to act before your distribution packages the fix, which sometimes means building from source or applying patches manually. And always test your backups before applying major updates. Updates can occasionally break things. If that happens, you need to be able to restore quickly, but never use the theoretical risk of an update causing issues as an excuse to stay vulnerable. The math strongly favors patching. Those 5 mistakes, wrong port, root login enabled, password authentication, no intrusion prevention, outdated software, are responsible for the majority of SSH compromises. Fix those, and you're already significantly better off than most servers on the internet. But while we're here, let's talk about additional layers that take your security posture further. Two-factor authentication for SSH is one that doesn't get enough attention. Even with key-based authentication in place, adding a second factor creates another barrier. Tools like Google Authenticator or Duo can be integrated with SSH via PAM. The flow becomes present your private key, then provide a time-based one-time code from your phone. Someone who steals your private key file and cracks your passphrase still can't get in without physical access to your authentication device. The implementation adds a bit of complexity, but the security benefit is real. Firewall-level IP restrictions are worth considering if your access patterns allow it. If you consistently access your servers from a fixed IP range, a corporate office, a VPN endpoint, you can configure your firewall to only accept SSH connections from those sources. An attacker who finds your SSH port and somehow obtains credentials still hits a wall because they're not coming from an allowed address. This doesn't work for everyone, but if your situation permits it, it's one of the strongest controls available. Rate limiting at the SSH daemon level complements fail2ban by operating at a lower layer. You can configure your server to limit how many unauthenticated connections it accepts per time period, which slows brute force attempts even before fail2ban's log-based detection kicks in. Think of it as a speed bump before the bouncer. Disable empty passwords. This should already be the default, but verify it. In your SSG config file, permit empty passwords should be set to no. If any user account on your system has an empty password and this is set to yes, anyone can log in as that user with no credentials at all. Check it, confirm it, move on. Cipher and algorithm hardening is another layer most people skip. SSH supports a range of encryption methods, including some older ones with known weaknesses. Algorithms like DES and RC4 should be explicitly disabled. Configure your SSH server to use only modern strong ciphers, AES in its various modes, CHA20, Poly 305. Restrict your MAC algorithms and key exchange methods to current recommendations. This prevents an attacker from negotiating a weaker encryption method that they can break after capturing the session. The OpenSSH documentation and resources like SSH Audit can help you identify exactly which settings to change. Logging and monitoring is where a lot of otherwise security-conscious administrators fall short. Knowing something happened after the fact is better than not knowing, but real value comes from being alerted quickly. Configure your SSH server to log all authentication attempts, both successful and failed. Then set up monitoring that actually notifies you when thresholds are crossed. Repeated failed attempts from a single IP, successful logins at unusual hours, logins from geographic locations that don't match your normal patterns. All of these are signals worth acting on. The faster you detect anomalous activity, the more options you have. For larger or more critical infrastructure, a bastion host architecture is worth serious consideration. Instead of exposing production servers directly to internet SSH traffic, you put a single hardened gateway machine at the perimeter. Administrators connect to that machine first, then use it to hop to internal systems. The bastion is the only server with port 22 exposed externally. You concentrate your security controls, monitoring, and logging on that one system, and your internal servers can be completely isolated from direct internet access. It creates a choke point that gives you much stronger visibility into who's accessing what. Finally, audit regularly. Not just when you're setting things up, but periodically. Review your SSHD config, check which user accounts have SSH access, rotate SSH keys on a defined schedule, remove access for accounts that are no longer active, former employees, decommissioned service accounts, temporary access that was never cleaned up. Security configurations drift over time, especially on servers that multiple people have touched. A quarterly review catches things that accumulate between audits. Let me give you one more example of what the failure mode looks like. A university research computing environment with hundreds of researchers needing SSH access. The IT team figured that since it was an internal academic network, the risk was low enough to not bother hardening the defaults. Then someone clicked something they shouldn't have in an email. Their laptop got infected with malware that scanned the internal network, found SSH servers on port 22, and launched automated brute force attacks against them. Several accounts had weak passwords. Within hours, the malware had foothold on multiple servers. Ransomware went out across the research storage systems. Years of work, datasets, models, papers in progress, encrypted. The university paid. Some data came back, some didn't. All of it because the baseline SSH security work had never been done. Here's what I want you to take away from this. These aren't advanced topics. You don't need a security background or deep cryptography knowledge to implement any of this. Change the port. Disable root login. Switch to key-based authentication and turn off passwords. Install fail2ban. Keep your software updated. That's the core of it. Most servers that get compromised via SSH weren't targeted by sophisticated adversaries. They were caught by automated tools looking for exactly these unaddressed defaults. When you're done making changes, test them. Try logging in as root. It should fail. Try authenticating with a password after disabling password authentication. It should fail. Deliberately trigger fail2ban with failed attempts and confirm it bans your test IP. Don't assume your changes worked. Verify them. Document what you've done. Write down your custom SSH port. Note where your keys are stored. Record your failban configuration. Store this somewhere secure but accessible. A password manager, encrypted notes, anything you can get to in an emergency. I've seen administrators lock themselves out of servers because they changed the port, forgot the new number, and hadn't written it down. That's a recoverable situation, but it's an entirely avoidable one. If you're managing multiple servers, look at configuration management tools like Ansible. Defining your SSH hardening as code means you can apply it consistently across your entire fleet, version control it, and audit it like any other codebase. Manual configuration is error-prone at scale. Automation removes that error surface. Security is an ongoing practice, not a one-time configuration. The threat landscape shifts. new vulnerabilities emerge. Attackers develop new techniques. Staying current means following security advisories, reading about new attack methods, and periodically reassessing whether your current setup still reflects best practices. What was solid configuration a couple of years ago may have gaps today. The effort involved in all of this is genuinely not large. An hour of focused work to implement the core settings, a few minutes a week to stay on top of updates, occasional reviews to make sure nothing has drifted. Compare that against the cost of a compromised server, the cleanup time, the potential data loss, the reputational damage, the possibility of your infrastructure being used to attack others. There's no reasonable argument for skipping this. If you found this video helpful, don't forget to like, subscribe to Nolan Tech, and turn on notifications so you never miss future tech videos. What's the first SSH setting you're going to lock down on your server after watching this?